Graph W is shown in the following diagram. The vertices of W represent tourist attractions in a city. The weight of each edge represents the travel time to the nearest minute between two attractions. AF has an unknown travel time x minutes. Question A. Write down a Hamiltonian cycle in W, 1 mark. What is a Hamiltonian cycle? To visit all vertices once and we start and finish at the same vertex. It is not specified at which we should start and finish, so let's choose for example A, and from A it may be to B, then to C, it's 3, or actually weight is not required here, to C, then to D, then to H, then to G, H to G, then to E, to F, and to A. For example, like this. The next. Daniel plans to visit all the attractions, starting and finishing at A. He wants to minimize his travel time. To find a lower bound for Daniel's travel time, vertex A and its adjacent edges are first deleted. BI. Use Prim's algorithm, starting at vertex B, to find the weight of the minimum spanning tree of the remaining graph. You should indicate clearly the order in which the algorithm selects each edge, 5 marks, and A is deleted and adjacent edges, and we started B, and we choose the edge with the least weight, and from B, because we start at B, it's what is BC, and weight is 6. And if you use the Prim's algorithm, the next edge to be considered, it should be the edge which is already connected or adjacent to the existing network or graph, and from B or C to be adjacent to the existing BC, it's what? It's CD. It's CD. So the next is CD and weight of 5. And actually, what is the minimum spanning tree? You may just imagine that there are computers B, C, D, E, H, G, H, and they should be connected in the network, or so that the length of the cable used is as least as possible. And we can see the edges from the existing edges, so from B, from C, from D, so that we can connect another vertex, and you can see it's DE, it's DE and 6. Then you can see it's BH 7, then definitely G can be connected to H, so GH and 4, and you can see there is only one remaining vertex, it's F, and the least weight of the H, it's what? It's 5, so it's it becomes F, G, and 5. And you can see that all vertices or all computers are already are connected in network, and the weight is just adds all these values up to get what? 11, 17, 24, 28, and 5, it's 36. 3. So weight of our the minimum spanning tree is 33, and it's required for the next question. And the next is, hence, for the case where x is less than 9, find a lower bound for Daniel's travel time in terms of x, 2 marks. And lower bound, it's the weight of the minimum spanning tree plus 2 edges from the deleted vertex, and x is less than 9, and you can see that there are only 2 vertices, so there are only 2 edges from A, so definitely it's plus 3 plus x, and it becomes 36 plus x in terms of x. The next, Daniel makes a table to show the minimum travel time between each pair of attractions. Question C. Write down the values of P, Q, and R. Let's consider what are the values of P, Q, and R. P, it's the distance from C to G. Definitely it should be of the least weight from C to G. From C to G, and just by inspection from C to G, from C to G, and it seems to be this way, CHG, and 9 plus 4, 13. May be required, let's write the actual root, so it's actually CHG, and it's not required here, but may be required for the next question. So let's write CHG, and it's what? It's 13. Then what is Q? Q is D, F, F, D, and again just by inspection you can see without X, and it seems 6 plus 11 to be the least possible distance, so it's actually DEF, and 17. And R, it's together with X from D to F, and it seems to be like this. So it's what? 11, 14 plus x. So it's 14 plus x. The next, to find an upper bound for Daniel's travel time, the nearest neighbor algorithm is used, starting at A. Question D, consider the case where x is 3, x is 3, x is 3, and DI use the nearest neighbor algorithm to find 2 possible cycles, 3 marks, and then find the best upper bound for Daniel's travel time, 2 marks. So for to find the best lower bound, you should take the value which is as large as possible, and for the best upper bound it must be the least possible value. So we should use the nearest neighbor algorithm starting at A, and from A the edge to some vertex with the least weight, and you can see that it's B, but also you can see it's also F, it's also 3, so as one weight we can use AB and something, and the next which can be considered is AF and something. So let's consider from A to B, and distance or weight is 3. Then according to this algorithm we'll consider B, and we need the weight, the minimum weight to any other vertex. And from B we can use a table, and from B you can see that it's to C or to F. Actually also it's another possible cycle. And actually when we construct such a table where all possible pairs are considered, such new graph will be complete, and complete graph definitely contains a Hamiltonian cycle. Actually, in fact, some vertices will be visited twice or more. So from B, let's choose C, and from B to C it's 6. C. Then we can see this C, and from C it's 5 to D. To D. From D you can see 5, but it's for C, but C is already exists. So from D to E it's 6. D, E, 6. Then from E you can see the list value is 8. It's to G. From E to G is the direct route. To G, E, G, 8. Then from G definitely to H it's 4. You can see that from G to H is 4. And you can see that there is only one remaining vertex, it's F, and the list and we can see the H, because the H, and from H we need only F additional to be connected, so we can see that from H to F it seems to be this H directly, but let's check. From H to F, from H to F, yes, there is only one actually variant, it's 8. So F8, and again to A it's X, and X is 3, so weight is 9, 14, 20, 28, 32, 40, and 43. Another possible cycle, it's again A, but we choose F instead of B, so it becomes AF, then from F, the shortest possible edge, from F, you can see that it's G. From F to G, so AF it's 3, it's 5 to G, then from G to H is 4, then from H to B, it's 5. You can see that from H Y5 it's 7. From G to H definitely the least possible value, it's 4. Yes, from H to B it's 7. Then from B, you can see that from B it's to C, from B to C and 6. Then from C to D it's 5, CD 5, CD 5. Then from D to E, from D you can see that to E it's 6, from D to E it's 6. Then from D to E, and you can see that it's the last one, and we need from E again to the starting point to A, and from E to A the shortest route it's 3 plus 11 or 14, and it's through F, so it becomes actually EF A and 14 in total, and weight becomes what? 8, 12 plus 7, it's 19, 25, 30, 36, 50, so 50. It's 50, and as best upper bound we should choose the lower value, so upper bound is 43. The next question E, consider the case where x is greater than 3. I, find the least value of x for which the age AF will definitely not be used by Daniel 2 marks. Now it's not 3, just x, and AF directly it means directly AF, and it will be not used when x is greater than this, when it's for example 19 or greater. We choose what? AF, which is 18. AF, A. From A to F, some another route which is less than the direct edge, which is 19. So x is 19. E I, x is 19. The next, hence state the value of the upper bound for Daniel's travel time for the value of x found in part EI. So for this x, which is 19, we need the value of upper bound, and our best upper bound is this one, but here you can see that this direct route which is 3, which is x, is used, but now this is not 3 and now it's 19, and it means that to move from F to A we should choose not x, which is now 19, we should choose what? This 18. So now this value is 19, and definitely we should choose, and there are two variants, 18 and 19, and definitely we choose 18. So this upper bound becomes 43 minus this 3, but plus 18, and it becomes what? 58. The next, the tourist office in the city has received complaints about the lack of cleanliness of some routes between the attractions. Karin, the office manager, decides to inspect all the routes between all the attractions starting and finishing at H. The sum of the weights of all the edges in graph W is 92 plus x. Karin inspects all the routes as quickly as possible and takes 2 hours. Everything is in minutes, so 2 hours, 120 minutes. It's actually total weight. And question F, find the value of x during Karin's inspection. So this question about what? It's about to visit all edges, definitely with total, with minimum total weight, and it's about Eulerian circuit. And a graph, to have an Eulerian circuit, all vertices must be of even degree, and here you can see that B and what D, BD, G and H are of odd degree. And this graph, to become Eulerian, we add edges so that B, D, G, H become of even degree, and a new graph will be or will contain Eulerian circuit. But in fact, some edges will be visited twice. And what should we do next? We should consider pairs. What? BH plus DG, BD plus GH, and what? BG plus DH. And by inspection we need the least possible distances, or the least possible weight, and BH, where is BH? BH definitely it's 7, DG, it's 14. Actually table can be used. It's 14, so it's 21. Then BD, where is BD? BD definitely it's 11. BD plus GH it's 4, so it's 15. And BG, where is BG? BG, it seems to be 11. Yes, it's 11. And BG plus DH, where is DH? DH it's 10, so it's 21. And we choose the least weight, it's 15, so it's BD. So BD, and BD, which is 11, it's actually what? BCD, so it becomes like this, and plus 4 this. And now our new graph with added edges becomes Eulerian, and there will be Eulerian circuit, but in fact some edges will be visited twice. And now you can see that all vertices are of even degree. And find the value of x. And it is given that the total weight is 92 plus x of all edges, but there are added, so plus 11 plus 4, because they will be visited twice. Or if we consider a new graph, so a new graph, it's the sum of all previous edges plus added edges, so total weight becomes this, and it is given that it's 120, and just x is required. Just solve for x, and you can see that x is 13. And that's all for this question.